Hello, hello. Yes, we welcome you back to PSSB, Physical Sciences, Silver Bullet, and it's me, Richard, here. Okay, tonight we are looking at this question. The question comes from a grade 10 topic, waves. Okay, let us explore the question. It says, briefly explain each of the following. What does it say? Speed of sound is faster in solids than in liquids and gases. Okay. And how do you explain that? Okay, here to explain, the explanation here is based on the fact that sound waves is a physical waves requiring a medium to be propagated. So when the particles of the mediums are closer together, sound waves tends to be faster because transmission of it from one particle to the other is faster. So it so happens that solids have closer particles compared to the liquids and gases. Hence, the transmission of sound waves in solids is faster compared to the transmission in liquids and gases. Okay, let's put that one down. So that is that. Then comes the next question. It says that the speed of sound is faster in summer than in winter. Yes. How do we explain this? Here the answer lies in the kinetic theory. According to kinetic theory, when the temperature is higher, the particles are moving faster. And we know that when the particles are moving faster, they transmit sound faster. So summer tends to have higher temperatures. And so the particles are moving faster, having greater kinetic energy compared to the winter. And so the transmission of sound is going to be faster during summer. Okay, let us put that one down. So that is that. And then we go to the next question. Let's look at it. So next question comes and it says, what is an echo? What is it? Technically, an echo is a reflected sound. Okay. So when sound is made and is propagated, when it strikes an obstacle, it bounces back from where it's coming from. It was coming from initially. So that sound which is coming back is what we refer to as an echo. Let's put that one down. So that is that. Then comes the next question. It says that briefly explain the application of an echo in, okay, one, sonar, or sound navigation and ranging. That's the acronym for sonar in ships. What is the application of echo in the sonar system of ships? Okay, this is what you have to know about sonar system. Sonar system has a transmitter of sound and a receiver of sound. So what happens is that the transmitter sends sound and the sound goes down, it hits the seabed and it is reflected. The reflected sound is picked up by the receiver. So the sonar system has a circuit which integrates the time of travel and it using also the speed of sound in water to compute the depth of the sea. So sonar systems generally are used to map out the depth of the sea, to determine the depth and also to know the obstacles around it. So let us put that one down. So that is that. Let's go through it. And used to determine the depth of the seabed. Sound waves are transmitted to the seabed, then reflected back as echo. Then use is made of the speed of sound in water and the time taken to calculate the depths of the sea. So generally, that's the work of the sonar, to map out the environment of the ships, of the ship. Okay, from there we are going to look at the next question. Okay. Then comes the next question. It says that briefly explain the application of an echo in birds. Okay, how is echo used in birds? Okay, we have to know that birds have poor visibility during day. They normally hunt for food at night. So what happens at night is that birds send sound, normally sound of very high frequency, which we can't even hear. And that frequency hits the object and bounce back. So within the birds, there is that ability to integrate the time taken and the speed of sound to know the distance of the object. So that's how they use it, to discern the environment by using the echo. Okay, let us put it down. So that is that. This process where the bats make use of the echo to discern the environment is called echolocation. Technically, echolocation is similar to sonar. They both involves integrating the speed of sound and the time to determine the distance. Okay, with that, let us go to the next question. So there comes our next question. It says that a sonar system in a ship sends sound waves to the bottom of the ocean. The reflected sound, which is echo, is received after 4.8 seconds. The speed of sound in water is given 1,450 meters per second. And the question says that calculate the depth of the ocean. Okay, how do you tackle this question? Here you have to know that sound is like any other physical object, like a car or any other object which is moving. So this question, we are going to use the normal equations, which says that distance is equal to speed times time. Some people actually prefer to put it as speed is equal to distance over time. Okay, but here there's something we have to remember. We have to remember that when sound moves, this is the trend. It is sent from the sonar. It goes to the seabed. It hits the seabed, which acts as a barrier now, and then it's reflected back to the sonar system. So when you analyze that movement, what have you noticed? That sound has traveled twice in that period of time given. And because of that, this equation, when it comes to echo, it changes. It becomes 2D equals to S times T. Or for those who prefer the other equation, S is equal to D over T. Thank you. So from here, what do we know? We know some of the physical quantities. What do we know? We know the speed of sound in water, which is 1,450 meters per second. What else do we know? We know the time, which is 4.8 seconds. So what do? We just have to substitute. So we are going to say 2 times distance, which we are looking for, is equal to speed, which is 1,450, times time, which is 4.8. From there, what do we know? We are going to say D is equal to 1,450 times 4.8 over 2. So what we have here is going to give us the depth of the ocean. Let us find it out. So that is that. The depth of the ocean is 3,480 meters. And with that, would like to thank you for your time. The channel is PSSB, Physical Sciences Silver Bullet. See you next time. It's me, Richard, here. Don't forget to subscribe. Don't forget to click the like button. And we see you next time. Bye-bye.